Hello, everyone. This is section 6.6 on surface area. We just did 6.5, so 6.6 is the natural next one to go for. And it's very related to 6.5, which is going on arc length. But instead of doing arc length, now the title suggests we're doing something a little different, and it's surface area. And it's actually combining a couple prior sections together, specifically about revolving around an x-axis or a y-axis, but looking at area instead of volume. So moving into it, the formula we have is let f be a non-negative function, has to be non-negative, and have a continuous first derivative on the interval ab, some random interval. The surface generated by revolving around the x-axis, or revolving the graph of f on the interval ab around an x-axis or a y-axis, we'll get to that in a second, has a surface area that is determined by this following formula. Your surface area is the integral from a to b, 2 pi times f of x times the square root of 1 plus the derivative squared dx. Now, hopefully, if you saw the prior video that I just recorded, this part looks very familiar, because if we remember arc length, the arc length formula was the integral from a to b of just that square root prime of x dx. So arc length and surface area are related to each other as formulas, which is kind of nice. Now, why is this true? Or why is this formula true in its own right? So again, let's create some random curve like this, and let's say it's from some A to B, like so. And again, we're rotating around the x-axis here, so let's just like put a little rotating arrow like so. So your corresponding shape, when we rotate this curve around the x-axis, will probably look like some sort of bowl, like that, right? And we will want to know what the surface area of this is. And the surface area is somehow determined by the length of this curve times something. Well, if we were to compare it to something we already know, imagine if instead we had just a straight line here like this, and then rotated that straight line. Maybe I'll do it on the graph here, and rotated this straight line along the x-axis. You would end up getting a cylinder, like so. And if you look it up online or whatever, the surface area of that round part of the cylinder, not the two faces, but the round part, maybe this is worth saying, of cylinder is 2 pi r times height. Where r is going to be this, and height is going to be whatever the length is of the cylinder, like so. And notice how this has a very similar look to our formula here, where we have some sort of term here, some sort of term here times 2 pi, some sort of term here, some sort of term here times 2 pi. And in fact, let me move this over here for a second. If I took some sort of small slice like that and rotated that small slice around the x-axis, like so, it might be a little weird seeing it here, but you have a little bit of curve on the side. But if you go smaller and smaller and smaller, that's going to look more and more like a cylinder. So in this situation here, we have a cylinder that has a small length, and that length here, or the height maybe in this formula, is captured by that length of the arc on that interval. And we just showed last video that the length of the arc is that 1 plus the derivative squared, all square rooted. So that's this length here in this part. And our height, or not our height, our radius would be essentially determined by whatever x is. If you got closer and closer and closer and shrunk that interval more and more and more, it ends up being whatever the height of your function is at that x point. So that is where this comes from. So when we say surface area is an integral between a to b of this 2 pi f of x times this here. We have that this f of x represents a radius of the small cylinder we created. I can't spell cylinder, and that's okay because I'm a math major. And then this is the length of the small cylinder. And now we have a sum of things or an integral of things, which essentially is just boiling down to, we've seen this in probably Calc 1, but also the last class, where you have a bunch of these small cylinders here. Those are also very bad cylinders, right? But adding them together throughout that entire interval, limiting the end goes to infinity, getting smaller and smaller cylinders together creates this integral formula. So I'm just going to put summing all, I'll put tiny in quotation mark, tiny cylinders together. And then that gives us a happy face because that is the formula that we started with here. So that is why we start with this formula in the first place. And note, I'll say around the y-axis, instead, like say we rotated it around this way, instead, you would get a totally different shape, right? This would look like kind of like an inverted cone. Kind of like that, actually. Ignore that middle slanted line there, rather than like a little bowl like we had before. It's the same idea. It's just that your radius is now going this way and your length is now going up and down. So you just got to recreate this in terms of like y's. So this would end up being integral from a to b of 2 pi. If you had some function in terms of y, you would put it in that function form times 1 plus g prime of y squared dy. And sometimes your formula changes a little bit depending on like the situation you're in. But what I always recommend for this situation, for a surface area in particular, if you are able to draw it out, you can usually see, oh, what's my radius supposed to be? My radius is supposed to be f of x in this photo. Or what's my length supposed to be? Well, my length is going this way, which means my length is more connected to a distance with 1 plus f prime of x squared rather than like some other version. Usually this part doesn't change as much. But okay, let's look at some examples now. So find the area of a surface generated when the given curve is revolved around about the given axis. So we have a function, we have an interval, and we're revolving around the x-axis. So around the x-axis, we have that formula. Let's just write that out here again. I'll write it over here. Your surface area is an integral from -1/2 to 1/2, since those are our bounds here, of 2 pi f of x is, let's just write it all out. F of x square root of 1 plus f prime of x dx. F prime of x, if f of x is equal to square root of 1 minus x squared, f prime of x, here, actually, let's get rid of the square root and put it as a 1/2. This helps me out, at least. 1/2. F prime of x, taking the derivative, now it's a chain rule problem. Remember chain rule from last semester? We're going to pull this 1/2 down, get 1/2, 1 minus x squared to the -1/2 power, times the derivative of the inside, so -2x. That's a classic thing that students mess up in general. So if you're thinking of doing a mess up problem in the assignments for this week or next week, think about messing up chain rule. That's a good example there. But this ends up looking like what? The 2's cancel, so we get negative x over square root of 1 minus x squared. So if that's what we have here, and also we're squaring this because it's a squared formula right here. Oh no. Oh no, good thing I caught that. And then we just go for it, right? So this is 1/2 to negative 1/2 here. 2 pi f of x is the square root of 1 minus x squared times the square root of 1 plus, if we're squaring this, you're going to end up getting x squared over the square root of 1 minus x squared squared, which cancels the square root to give us 1 minus x squared dx. And it's like, oh, yay, we did it, right? But again, we've set up the formula. Now it's all about cleaning it up so you can integrate it. Right now, it's really tough to integrate, right? So let's see what we got here. This will end up becoming, let's see if I can clean this up a little bit. A classic way to clean it up would be to get a common denominator on the side, or you can factor out that however you want to do it. I'm going to do the common denominator and change this 1 into a 1 minus x squared over 1 minus x squared. And notice, if this is 1 minus x squared over 1 minus x squared, which again is 1, this common denominator means I can add across, which means these x squareds on the numerator would cancel. And I'm left with just 1 over 1 minus x squared in that integral here. So let's just write that out right here. 1 over 1 minus x squared here. And this will be the integral from negative 1/2 to 1/2 of the square root of 1 minus x squared. So all of this right here actually just became this dx. And let's not forget our friendly little 2 pi here as well. I'm kind of all over the place right now, right? But one thing that's super nice in this problem is that we have a 1 minus x squared square rooted in the numerator and that same thing in the denominator. So those things end up canceling out, and we're left with just square root of 1 or 1. So this is integral from negative 1/2 to 1/2 of 2 pi dx. Oh, that's awesome. Look how much that cleaned up. We started with this ugly thing, and just one little switch around ended up giving us just a constant to integrate. And constants are my favorite thing to integrate. I don't know about you guys, but bam. Now that's a good integrate right there. When you start adding this all up, you're going to get 2 pi times 1/2 minus negative 1/2, or adding it together to get 2 pi. So that is your answer here. I have that this is going to be our star question, so make sure you write this neater than even I wrote it because I had a little bit less room than I was expecting here. But I have a question for it. Question: why was this number expected for this problem? And I'll give you a hint. Graph it on Desmos. Graph on Desmos. Click, type in Desmos on the computer, graph that function, see what that looks like, and visualize revolving it around the x-axis. What is that going to look like when you end up revolving that around the x-axis? This should be a shape you recognize, and you should know, or at least even be able to Google the surface area of a shape like that. So I want you to write a sentence or two saying why this answer is expected for a problem like this. We didn't have to do calculus. We just ended up doing calculus. Okay, so now let's do a version where we go around the y-axis instead. So we can do both versions here. So find the area of the surface generated when the given curve is revolved about the y-axis, and this is our curve here. And if we're revolving around the y-axis, let's even draw this a little bit here, right? We have x equals 2 to 4, and it's like a parabola, so it looks like this, from 2 to 4, and we're rotating it around the y-axis here. So we're going to end up getting like a bowl in that direction. Our functions rotating around the y-axis have functions in terms of y instead of in terms of x's. So we're going to need to change this to be like x equals something and get everything in terms of y instead of this in terms of x. And the way to do that is pretty easy. I just have 4y is equal to x squared, square rooting both sides. I'm going to have x is equal to 2 square root of y, like so. Really, it's plus or minus, but our values are all plus from 2 to 4. So we would take the positive version here. Okay, and if x is from 2 to 4, we need to get our bounds in terms of y as well. This is also a very popular mistake. People just leave the bounds as 2 to 4, when really we're going to be having y as our variable now, so we need y to be our bounds. So when x is 2, what is y going to be? When x is 2, it'll be 2 squared, or y will be 1. When x is 4, 4 squared divided by 4, y will be 4 as well. Like so. So really, we should have had it like this at the start, and then we could do the same problem as before, but the problem gave it to us differently, which is okay. So we're going to use this formula again, but for the y-axis. So maybe I'll write it in as the integral from 1 to 4 of 2 pi g of y times the square root of 1 plus g prime of y squared dy. And let's see where we go from here. I know g of y is going to be this. So I already have that. G prime of y is going to be, this is where if my mom was here, I would be like yelling at her like, but can't do that right now. So let's move on from that. This is really y to the 1/2 here. Taking that derivative, it's going to end up being y to the negative 1/2, because when you bring that 1/2 down, it cancels. Squaring it is going to be y to the negative 1 power. So what does this give us? This gives us s is equal to 1 to 4 of 2 pi. G of y is going to be 2 times y to the 1/2, 2 times y to the 1/2, times the square root of 1 plus g prime of y squared is y to the negative 1, and then dy, like so. So let's just keep simplifying now. What is s going to be here? From 1 to 4 of 4 pi. Let's put the square root stuff together. I'm doing this kind of off the cuff as well, that this is going to be y1 plus y to the negative 1 dy. That's when I take this square root of y and this square root of stuff and just combine it together to be 1, which is a property you can do. So we get 4 pi times the square root of, distributing this over, we'll get y plus 1 dy. And actually now I'm going to move this back to be to the 1/2, like this. And normally in the formal process, the way I might have taught it in like a Calc 1 class, I would finish this off by doing a u substitution. But because it's such a simple u substitution of just u equals this y plus 1 to like finagle it all and get it how we want it, most of the time you don't have to do that. And they even teach you in prior classes not to do that and just like see what the antiderivative is by taking the antiderivative straight up. So this 4 pi gets on its own. And if you look hard enough and think about it, maybe pause the video or do a u substitution on your own, this antiderivative is y plus 1 to the 3 halves all over 3 halves, like that. And we can verify by taking the derivative real quick in our heads, right? If I take this derivative, I bring that power down, it cancels, and I subtract that power by 1, and I get exactly the same thing. This is from 1 to 4. So maybe we can go. We'll add another page, actually. I'll make it a little bit easier. No, we're not going to add another page. Let me fix this real quick, guys. Okay, so done with that. Let's add a page the better way. Booyah. I know how to use technology. So what does this end up equaling to? You flip it, so you're going to get 8 over 3 pi as your little collection of stuff right here. And then you're going to get 4 plus 1 to the 3 halves minus 1 plus 1 to the 3 halves. Or 8 over 3 pi 5 to the 3 halves minus 2 to the 3 halves. Now, you might know that off the cuff awesomely, but I don't, so this is going to be the good enough answer. And in like MATLAB and stuff like that, that'll be the more sufficient answer as well anyways. Like they will want you to put the exact answer like this. And that is it.